Hey guys, so in this video, we are going to talk about mathematics. And why mathematics? Because A, I like it, but B, and most importantly, because mathematics is the language that we have stumbled upon to describe the universe around us. It is the most precise language that we have to describe reality, right? And I think even more interesting than that, though that is very interesting in its own, more interesting than that is that we have also come across, we have thought our way through to the correct physics that allows us to use the mathematics that we can speak very well to actually implement or run, our mathematical models on computers, right? Computers rely on physics, but we can create mathematical models that can run very well on these computers, allowing us to have, the technological revolution that we're still on, at the current moment. We're still, in the revolution, I would say. But that is an interesting topic, and I'm happy to say that I will make a video on that topic alone in future. But right now, we are going to talk about straight lines. And I would like to sort of impart my excitement about these very unassuming mathematical entities, straight lines, on you. And by the end of this video, if I have succeeded, then I want you to be excited about straight lines as I have been in the past week or two. That being said, let's jump right in. Okay, before we begin our foray into the land of straight lines, I would like us to first ask a question. And it will become very clear by the end of this video why asking this question and then proceeding to attempt to answer it is very important. It's important in this sense. If you do understand the answer to this question in the form that I do present in this video, then you understand completely the main idea or the point of the video. Here's the question. Suppose you have a line y is equal to mx plus c. You then rotate this line about the origin until it is horizontal. What is the y-intercept of this new line? I think it's a very beautiful question, if I do say so myself. If you would like to reread the question or even attempt solving it, please pause the video now, because we're now looking at an animation depicting or describing what this question is about, really. So this is the special case where m, the gradient of the line, is 1, and c, the y-intercept of the line, is also equal to 1. And we're looking here at the line rotating really about the origin. So now the question is concerned about the brief period of time, or the instant really, the instant in time when the line is horizontal. So think about freezing the video when the line is horizontal. Either the line cuts the y-intercept above 0, at 0, or below 0. But this is a special case when m and c are both equal to 1. The question is interested in finding out what will the y-intercept be in general for a general m and a general c. That is the question. If your high school education was anything like mine, you would have learned that a straight line could be described by the relationship y is equal to mx plus c, where the two numbers m and c are the two numbers that are required to fully define a given straight line, or whatever straight line you wish to define. So what do the two numbers mean? M is the gradient of the line, which is simply a measure of how steep the line is. A bigger m means the line is steep or steeper. A smaller m means the line is more flat. And c is the y-intercept of the line, which really just means the number or the point at which the line crosses the y-axis being the vertical axis. Okay, at this point we should know enough about the problem, and we should have enough theory in our arsenal to start or attempt solving the problem. But as I've already said, that the punchline to this video is in the solution to the problem. But before we present the very elegant solution to this problem, I'd like us to first look at some not so beautiful solutions to this problem. So the first idea we'll consider relies on the idea of a matrix. And a matrix, if you've never come across one before, is nothing but a way of neatly representing equations.
Specifically here, we'll concern ourselves with a specific type of matrix that we call a rotation matrix. And a rotation matrix is nothing but an operator that tells us how vectors in a certain space change when they are rotated by some angle theta. So here we are looking at a rotation matrix which is used to rotate vectors in 2 dimensions. But how does that actually happen? It happens through matrix multiplication. Let's perform that on our problem and see what happens. But first, it is important to realize that every point on our line y is equal to mx plus c has an x-coordinate x and a y-coordinate y. So we represent points on our line as just x and y. So our rotation matrix acts on x and y, or multiplies the vector xy. But we know that every point on this line has y is equal to mx plus c. So we do the obvious thing and substitute mx plus c in the place for y. And at this point, we simply crunch the numbers and perform matrix multiplication and get what we get in the last line. And at this point, it's very important to pause and consider what we're looking at and what it means, right? So now what we started off with was an odd line, right, with x and y as its signature. Now what we're looking at is the signature of the new line, the rotated line rotated by some angle theta. This is the new line, and it has x-coordinate x cos theta plus mx plus c times sine theta, and the y-coordinate is minus x sine theta plus mx plus c times cos theta. Now that's very important to understand what's going on here, because it's going to be very, very important for the next step. And that next step is recognizing that we are looking for the y-intercept, and at the y-intercept, the x-coordinate is equal to 0. Therefore, we go on and set our x-coordinate equal to 0, and then we solve for x. But then, if we're looking for the y-intercept, we're interested in the y-coordinate. Therefore, we take this value for x, we substitute it into the value for the y-coordinate, and then we simply solve. Let's just call this y-intercept that we're looking for C star, and then we solve for C star. And there we have it. C star is the y-intercept of the new line we've been looking for. However, it should be independent of theta. And one way of eliminating this theta is to recognize that if we start at a point on the line, any point on the line, then we move 1 unit in the x direction, and then m units in the y direction, then we should land back exactly on the line. And why is this? This is because this is literally what it means for the line to have a gradient m. This means that for every 1 unit change in the x direction, there's a corresponding m units change in the y direction. And then we can use Pythagoras' theorem in the resulting triangle to find the hypotenuse. And now that we have this triangle, we can completely define what cosine of theta and sine of theta are. We substitute these back into the equation for C star, and then we solve for C star without the theta. Okay, so the second ugly solution to the problem that we're going to consider relies on a key observation. And this is the observation. When the line is eventually horizontal, there will be a line segment that will be perpendicular to this line. And obviously this line segment at this point will be vertical because the line will be horizontal. And the key is to realize then that the y-intercept, or at least the y-coordinate of the y-intercept, will be equal to the length of this line segment. And then the problem just reduces now to finding the length of this line segment. And we can do this if we do know the coordinates at the end points of this line. One end point is obviously at the origin. We know the coordinates of that. And then the other end point will be at the point of intersection of this line segment together with the line y is equal to mx plus c. Let's call this point P. Now let's go on and find the coordinates of point P. And finding the coordinates of point P is quite straightforward, right? Because we do have the two equations of the two line segments, and we do know that at P they share a point. Therefore, we equate their y coordinates, we solve for the x coordinate, which is common to both. And then once we have this x coordinate, we plug it back into the equation of the line segment to solve for the corresponding y of point P. And once we have that, then we can simply apply the distance formula to find the length of the line segment OP. And I won't go into much details about that, but the distance formula is nothing but, Pythagoras' theorem in disguise. So once you have that, you can do the numbers. You can just crunch the numbers until you get to the final result, which is exactly the same as the one we got for the ugly solution number 1. Now, let us look at the solution that makes the last 2 solutions look absolutely terrible in comparison. And I think this solution is particularly beautiful because it shows us that the answer to this problem all along was in the equation y is equal to mx plus c. All we needed to do was to look at the equation differently, look at the equation from another perspective, and we would find the answer. The intuition for this solution, however, relies on a bit of familiarity with the dot product and vectors and components of vectors, or linear algebra in general. But even if you are not familiar with these ideas, I'll try to make the intuition as clear as possible. So, we start off with the equation that we've been given, y is equal to mx plus c. And then we simply rearrange the terms such that we have y minus mx is equal to c. And this is the part where things start getting interesting. We can represent the left-hand side of the equation differently. We can realize that the left-hand side of this equation can be written as a dot product, or simply as a matrix multiplication of one vector transposed times another vector. The first vector is the vector minus m1, and the second vector is the vector xy. Now, if we do this representation, we have changed nothing about the equation. We have simply represented it differently. And we have to think very hard about what this new equation then means. You have to try to interpret what it means. And we can think of a dot product as really finding a component of one vector in the direction of another vector. But this is not entirely true until or unless the vector, one of the vectors of interest, is a unit vector. And what does a unit vector mean? This simply means that the magnitude of the vector is equal to 1. And we can achieve this, right, by simply dividing by the magnitude of one of these vectors that we would like to make it have a magnitude of unity. So we do that here. We divide by the magnitude of the vector minus m1. And a simple distance formula here will show you that the magnitude of this vector is the square root of m squared plus 1. Divide both sides by that.
And this is it. We've reached the solution to the problem. And the solution to the problem is the term that you see on the right-hand side of the equation. But the difficulty, of course, in this approach is trying to interpret what that equation means and trying to understand really why is that the answer. And let us try to do that. So let's try to interpret what that equation means. This equation is telling us that another way of looking at a line is to look at it as the set of all points xy, such that all these points have some component c over square root of m squared plus 1 in a particular direction that depends on the gradient. So a line is nothing but a set of points that, when resolved in a particular direction that depends on the gradient m, have a constant component c divided by the square root of m squared plus 1. And you have to think very hard and convince yourself that indeed all the vectors that are on this line of ours do have the same component in the direction of that red line segment. That is the punchline of this video. The difficulty is in trying to understand why that makes any sense at all. But once you do understand it, then it's such an interesting revelation. In order to drive this point home, let us look at 3 vectors that lie on this line.
And I want you to try very hard to convince yourself that all three of these vectors have the same component in the direction of that red line segment, including the red line segment itself, since the red line segment itself points to or is a vector that lies on the line. Therefore, the red line segment itself has a component in the direction of itself that is equal to c over square root m squared plus 1. And if a vector in the direction of itself has that component, then that means it has the magnitude equal to that. The magnitude of that red line segment is therefore equal to c over square root m squared plus 1. And as we've argued in the previous solution, that is exactly what we're looking for. We're looking for the magnitude of that red line segment, which is equal to c over square root m squared plus 1. I guess what I'm arguing here then is that there is an alternative way of looking at lines, right? And this way of looking at lines has nothing to do with gradients and y-intercepts, but it has to do with a direction and the magnitude or a component, right? So you can think of any straight line, at least in 2 dimensions, as the set of all points xy, such that the component of all these points in the direction of some unit vector, let's call this unit vector c hat, is equal to some real number b. That's what I'm arguing for here, that I'm not saying let us abandon the way of looking at lines as y is equal to mx plus c, because quite frankly, looking at them in this arithmetic way is easy, especially for someone who doesn't have the background that we need in order to understand this new approach of looking at them in terms of factors and dot products and components. So the y is called mxc way is quite introductory, so it's great if you are teaching this to high school students. But then if you want to maybe reap more out of your understanding of straight lines, then you would also need to consider this other way of looking at straight lines. In fact, I think this other approach is great because it even allows us to talk about lines not only in 2 dimensions as we are here, but in higher dimensions, right? There is no restriction on how many components this vector x should have. You will have realized that in this example, it had 2, right? It had x and y, but you can go to 3 dimensions and talk about x, y, and z. You can go to 4 dimensions. You can go to however many dimensions you care about, right? So this is one of the benefits of looking at this, of looking at things this way, I would say. And in closing, I will just look at an example of a place where this is useful. So if you're the kind of person who likes to be convinced by applications of something, then we'd look at a practical real-world application of this perspective. Of course, this representation of straight lines is not original to me. In fact, I came across this way of looking at straight lines while I was studying classification algorithms. And I was like, whoa, I thought I was a fairly educated man. Why have I not come across this representation of straight lines before? And I found it very interesting. So this example that we're looking at here is a classification problem, right? Imagine you are a student working in a lab and you find a cell, but you are scared of asking your professor whether it's a white blood cell or a red blood cell because you're scared they'll think you're stupid. So instead, you decide to build a classifier for yourself so that you can be able to classify this cell and any other cell in the future. Luckily for you, in the lab, there are already other cells that are already labeled for you as red or white blood cells. Now you take these cells, you measure 2 parameters from these cells. Again, this is a heavily contrived example, but let us assume that these 2 parameters you measure are weight of the cell and say the thickness of the cell. Once you've done those measurements, you then plot the data, and this is what you get. It is quite obvious to the human eye that here we have 2 classes of data, and a straight line is a good candidate for a discriminator. In fact, this is what support vector machines do. So your task in building a classifier then becomes determining the appropriate straight line or an appropriate straight line, which in other terms is simply finding out an appropriate c hat and an appropriate value of b that defines a straight line that separates your data into the 2 classes. Once you've determined your C hat and your B, then every cell that you meet in future is simply a data point or a vector X, right? And that cell can be classified simply by taking the dot product of that vector with C hat. So all white blood cells that you see here will have C hat dot X less than B. And all red blood cells will have C hat dot X greater than B. And all points that lie on the line will have C hat dot X equal to B, right? So this is how we're then able to classify each and every other cell in future by computing C hat dot X. If C hat dot X is less than B, then we conclude it's a white blood cell. If C hat dot X is greater than B, then we conclude it's a red blood cell.